Welcome to the deep dive. Today we're tackling a really big one, Einstein's general theory of relativity.
Yeah, it's definitely mind-bending stuff. You shared some great research covering, well, pretty much everything from its history to current frontiers.
Exactly. And our mission today is, to unpack this a bit, make sense of how it totally rewrote the rules on gravity, space, and time.
Right. Forget Newton's idea of gravity as like a force pulling things. Einstein said, no, gravity is actually the shape of space-time being curved by mass and energy.
Okay, the classic analogy is the bowling ball on a trampoline, isn't it?
That's the one. The heavy ball warps the fabric, and that warping tells other smaller objects how to move.
So the Earth, being massive, creates this dip, this curve in space-time around it.
Precisely. It creates a gravitational well. We're not really being pulled down, we're following the curves. Even light follows these curves.
So objects in free fall, they're just taking the shortest path available to them in this curved geometry, like a geodesic.
Exactly that. It's the straightest possible line on a curved surface. And this leads to what Einstein called his happiest thought.
Ah, the equivalence principle.
Yes, the idea that you can't distinguish between the feeling of gravity and the feeling of acceleration. If you're in free fall, you feel weightless. It basically equates gravity with acceleration.
It's such a radical shift. So, okay, how did he go about proving this? What were the big predictions?
Well, a major early one was the bending of light. He predicted that gravity, specifically a massive object like the sun, should actually bend the path of light passing near it.
And wasn't there a famous observation during an eclipse like 1919?
That's the one. Arthur Eddington's expedition. They measured starlight bending around the sun, and the amount, about 1.75 arc seconds, matched Einstein's prediction perfectly.
Which was different from what Newton would have predicted.
Significantly different. Newtonian physics predicted only half that bending. So it's a huge win for general relativity. We see this now with gravitational lensing too. Galaxies bending light.
Wow. Okay, and besides light bending, there's something weird with Mercury's orbit.
Right. For years, astronomers knew Mercury's orbit wobbled, it precessed, a tiny bit more than Newton's laws could account for. About 43 arcseconds per century discrepancy.
Just a little bit off.
A little bit, but persistently off. General relativity, when you factor in the sun's warping of space-time close-up, nailed that extra 43 arcseconds exactly.
Solve an old mystery. And then the prediction of gravitational waves. Ripples in space-time itself.
Yeah, ripples caused by really massive objects accelerating, like black holes colliding. Einstein predicted them way back.
But detecting them took a while, right?
Oh, absolutely.
Wow.
We had indirect evidence from observing binary pulsars like Holson-Taylor found, their orbits decaying, just as predicted if they were losing energy to gravitational waves.
Okay, indirect proof.
But the direct detection in 2015, announced in 2016 by LIGO, that was monumental. Hearing the chirp of two black holes merging billions of light years away.
Just incredible. And this stuff isn't just cosmic, it affects technology down here, like GPS.
Totally. General relativity predicts time dilation. Time actually runs slightly slower in stronger gravity. Clocks closer to Earth tick slower than clocks on GPS satellites.
And special relativity plays a part too, with their speed.
Exactly. You need both corrections.
Yeah.
Without accounting for these relativistic effects, GPS would be off by kilometers every single day. It just wouldn't work accurately.
So Newton's laws are like a good approximation for everyday stuff, but not the whole picture.
Pretty much. For weak gravity, slow speeds, Newton's great. But for precision, or for extreme gravity near black holes or cosmology, you absolutely need Einstein.
Speaking of those extremes, where is general relativity most crucial in astrophysics today?
Oh, everywhere. Understanding black holes, how they work, how they merge, neutron stars, the Big Bang itself, the expansion of the universe. Even studying dark matter through its gravitational lensing effects relies on GR.
And what's the cutting edge now? Where's the research heading?
Well, the biggest challenge is unifying general relativity with quantum mechanics. They describe different scales, gravity versus the very small, and they don't quite mesh yet. That's the quest for quantum gravity.
Like string theory or looped quantum gravity.
Those are the main contenders, yeah. Plus, trying to understand dark energy, the nature of singularities inside black holes, testing GR in ever more extreme conditions using things like gravitational waves.
It's amazing. A theory over a century old, still driving so much fundamental physics and even impacting our daily tech.
It really reshaped our entire conception of the universe, from the smallest scales of time dilation to the largest structures.
And the fact that it might not be the final word, that there might be something deeper connecting it to the quantum world, that's pretty profound.
Definitely. It suggests there's still so much more to uncover about gravity and the cosmos.
So, next time you feel gravity holding you down, remember it's space-time itself, warped by our planet. Maybe thinking about that geometry offers a new way to see our place in the universe. Thanks for diving deep with us today.